and today I'll be using homogeneous linear ODEs with constant coefficient to understand suspensions in cars. As you can see here is a picture of a car suspension. Here's how suspension will work. So here we are going to investigate the suitability of the car suspension with the new car. So let's start by understanding why car suspension is important for cars and their users. Basically, we need to understand the 3 C's, which is control, comfort, and contact. Control, we want to ensure that we have control over the car and the car does not swing to the left or swing to the right when you're turning right or left, for example. Comfort, you want to still feel comfort when you go over a bump, when your car goes over a bump. Then to make sure that your driving experience is a comfortable experience. And lastly is contact. Contact is to ensure that cars tires are all touching the ground throughout your journey, which is also very important for the safety of the user. This is a schematic of a car suspension. Basically, we have the mass of the car. Here we have the shock absorber. We have the spring. And we have the tire. So moving on, we can now try to understand the type of cases involving the ODE. So basically, case 1 we have underdamping, in which we have complex conjugate roots. So basically, we have normally a negative number, or normally, and see the negative number, we normally convert it to imaginary number I. And this is the equation to solve for my case for underdamping. It has complex conjugate roots. As you can see the word complex here. And this occurs when damping constant is so small, then beta is no longer imaginary. So case 2 is critical damping. The wheels are root. Normally we have only one root, same lambda 1 equals to lambda 2. And any slight decrease in damping force will result in oscillatory motion. Case 3, we have overdamping. We have two distinct roots, lambda 1 and lambda 2. And this is the equation here. And what happens is damping takes out energy so far that the system does not oscillate much. This will be further explained later on. So in discussing about our suitability of the suspension of the car, I decided to fix the mass of the car. This the total mass of the car is 1600, and I decided to basically the 4 corners of the car, and one corner will be 400 kg. The spring constant also of the spring will remain constant 1000 meter per meter. The initial displacement in testing out will be constant, also 0.15 meter. And the initial velocity will also be constant, 0 meters per second. So first case, I'll put my damping constant equals to 800. And then we can use this equation lambda square plus damping constant over m plus spring constant over m equals to 0 to find the equation. And just having the value 800 for damping constant, and then 1600 spring constant, mass is 400, so we get lambda square plus 2 lambda plus 4 equal to 0. I cannot factorize this, so I need to use this equation. And once I use the equation, I get lambda equals to -1 plus minus square root of -3. Since it's negative, I can put inside 3i. And now, since it's the imaginary number here, so I have to use this equation for find my general equation. And you see this negative a of t over 2, I just sub in a here is 2 lambda. So I sub in my value, I get negative t, so wo is square root 3. And because here is square root 3, and then you just sub inside a value here. And I know my yt equals to 0.5 and t equals 0, and dy over dt equals 0, and t equals to 0. So what I'll do first is find my derivative equation, which is this. And how I get it is product rule, where I let this be my u and this be my v. And once I get my derivative, I'll just sub in my values. Therefore, I'll get my a equals to 0.15 and my b is equal to 0.15 over the square root 3. And then I have to change it to a phase shift amplitude equation. So I get a squared plus b squared here. And then arc10 BOA, and this is my phase shift equation. So when I put inside a phase shift equation into the calculator, and I get this graph. So as you can see, this graph it takes some time to reach its equilibrium position, which is roughly here, but it looks like it's about to fluctuate again, as you can see here. So I want to see what happened if I reduce my damping constant. So basically, just use the same equation again. Lambda here, the same equation, lambda plus COM, lambda plus KOM equals 0. Then therefore I get this equation, lambda square plus lambda plus 4 equals 0, which cannot be factorized. So therefore I have to use this equation again, sub in, get this equation. To use this equation again, it's because I got an imaginary number here again, so it still remains in case 1 in the damping. So once I find out what's my a, negative 18 over 2, which is negative t over 2, my wa 15 over 2, got this, it's just sub it inside here, and basically I do the same step as the previous equation. I'm going to find my dy dt first before I sub in my values to find what is my a. So my a is 0.15. So you can see I still remain the same condition of t equals to 0, yt equals to 0.15. In this one also I'll get the same thing, because 0 sub in t equals 0, and my dy dt is equal to 0, and I'll get this equation. So I sub it inside back to find my solution, and find amplitude phase shift equation. Once again, square root of a squared plus b squared and arc10 BOA, and get this equation. So I put inside my calculator again to get a graph, and you can see that the triangle before the triangle is sort of moving around, and is not reaching the equilibrium position much. It's very bad because it shows the car can be shaky or very rough moving or something. Next, if I use critical damping. So in order critical damping, I make my spring constant to 1600, is here. And sub inside my equation, the same equation before, which is lambda squared plus COM lambda plus KOM equals to 0. So I get lambda squared plus 4 lambda equals to 0, which can be factorized to be x plus 2 and multiply with another x plus 2. So therefore my lambda becomes negative 2, and yt, which is, since it's only of one rule, so I used to use this equation to find what my solution equation is. So I find, once again, I found negative 80 over 2, which you get this. So a negative 2t, so I just put yt equals to e negative 2t a plus bt, and dy dt is equal to this equation. So when you derive this, remain the same rule, product rule. So this becomes my u, and this becomes my V. So I got this already, and I submit my values to find out my A. My A is still 0.15, and my B is 0.3, because when you sub in the values, you cancel this to say this is equal to 2, and this is gone, and this is A, so 2 times A, and you have a plus here, so a plus, and this is cancelled to be 1, so this B. So 2A plus B equals to 0, so B equals 0.3, because I already found my A up here. And therefore I can get this equation, which I just sub in my calculator to find my graph. And if you follow the graph, you can see the thing quickly turns back to equilibrium position, which is what car manufacturers want. And the last case is case number 3, which is damping case. So for damping case, I make my damping constant 3200. Use the same equation again, and so I substitute the value lambda square plus 8 lambda plus 4 equals to 0, which cannot be factorized. So I have to use this equation again, and I'll get lambda equals to negative 4 plus 2 square root of 3, which equals to lambda 1, get 2 lambda values, which is 0.536 and negative 7.464, and sub in your value for my yt equation. So yt equals to this, because lambda 1 here, lambda 2 here, t, multiply t, and then finally find my a and b. So if I differentiate, I get this using the chain rule, and submit my values for the initial equation. So y equals to t equals to 0, so t is 0 equals to 0.15, and get a plus b equals to 0.15, which will equal to my first equation, because later on I will need to do simultaneous equation. So when I sub in my for dy dt, put t equals to 0 equals to 0, so I get my 0 equals to this equation, which is my second equation. If you do simultaneous equation, that later on you will get this as your answer, b equals to negative 0.012, a equals to 0.162. So for my yt equals to 0.162 e to the power negative 0.536t minus 0.012 e negative 7.464t. And if I sub inside this into my graph, to my calculator, I'll see that this thing is actually taking more time to reach its equilibrium position here, and still haven't reached after the 5th second. So in conclusion, we can say that case 1, the amplitude or the graph approaches equilibrium after some time, but in case 2, the graph returns to the original position the fastest. Therefore, it is the one the car manufacturers desire. In case 3, it takes more time to return to its original position, which car manufacturers don't want. So therefore, a critical damping is the best for our car suspension. And lastly, if you follow back the previous slides, after I change the damping constant, we can see that it takes more time to get to equilibrium position, and the graph doesn't reach to equilibrium position fast enough. So good damping constant value should be considered when making a car.